Hello, it's Stat 134, Lecture 4. Just a reminder, you have a quiz on next Wednesday covering all of Chapter 1. So last time we talked about independence, and if you have A and B that are independent, then also A and B complement, or A complement and B are independent. And this follows from the argument written at the top here. We also discussed Bayes' rule. In particular, we finished the problem from last time where we left off. We needed to find the probability that Greg has brown eyes, given that the dad has genes capital B, little b. And the idea here is to condition on all the different possible genotypes of the mother. Namely, the mother could have little b, big B, little b, big B, little b. And we're just going to assume that all of those probabilities are a quarter. So they're going to weigh equally the probability of Greg having brown eyes, given the dad being heterogeneous and the mother being whatever it is that she is. So we're adding up here 4 conditional terms, and that all adds up to 3/4. And so then we can finish the problem where we were asked originally to find the probability that the mother has blue eyes, given that dad is heterogeneous and Greg has brown eyes. And we find that that's 1/6. So the probability that Greg has brown eyes, given the mother having blue eyes and the dad being heterogeneous, is called a forward conditional. We do not need Bayes' rule to compute this. And the probability that the mom has blue eyes, given that the dad is heterogeneous and Greg has brown eyes, is backward conditional. It's kind of backwards, right? Because you're asked something about the mother given what the son's genotype is. So this is also called a posterior conditional. We found it's 1/6, which updates the prior that the mother having blue eyes is having probability 1/4. Today we're going to go over the student responses of the concept test, section 1.6 on independence of 3 or more events, section 2.1 on the binomial distribution, and we'll start section 2.1 on consecutive odds ratios. So question 1, A and B, 2 events, probability of A is 0.5, probability of A union B is 0.8. Is it possible to have mutually exclusive and independent? And most of you got this right, that the answer is no, because again, the only way that we can have both of those is if A or B is the empty set, and that is not the case here. The second question had probability of A being 0.8 and a probability of A union B being 0.8. And here most of you got that it's correct that it is possible. So we don't know for sure because B may be a non-empty subset of A, but if it is mutually exclusive, then it would have to be independent. So it is possible. For independence of 3 events, we start off with the definition of pairwise independent, which just means that for any 2 of the 3 events, that those are pairwise independent, okay? And I give an example here where B12 is the chance that I have the same birthday as you, B13 is I have the same birthday as Mike, and B23 is the event that you have the same birthday as Mike. And so we can see that this is pairwise independent quite easily. However, we'll shortly see that B12, B13, and B23 are not independent. The definition of that is that A, B, and C are pairwise independent, but also that you have this factorization shown here. And a reason you can see that independence is stronger than pairwise independence, well, of course, it assumes pairwise independence, but also to have this factorization here, you must have, for example, the probability that C conditioned on A, B is equal to the probability of C. And that is not given by pairwise independence. So that is a stronger assumption. And so here we see that, in fact, this factorization doesn't work. For example, B12, B13, B23, that intersection is just the same as the intersection of B12 and B13. And we know the probability of that is 1 over 365 squared. And that's different than 1 over 365 cubed. So we do not have independence. We then define the binomial distribution. The binomial distribution has consists of n independent Bernoulli p trials, where n is some fixed number, p is a fixed unconditional probability, and a Bernoulli trial has just two outcomes: a success and failure, with the success having probability p. And so the binomial formula gives the probability of having k successes. And I give an example and I motivate that formula, but I'm going to skip over this because that was pretty clear, I thought. So we then did some tricky concept test here. So 10 cards are dealt off the top of a well-shuffled deck. The binomial formula doesn't apply to find the chance of getting exactly 3 diamonds because B, the trials aren't independent. The trials are not independent because if the first trial is a success, that affects the chance that the second trial is a success, because the conditional probability that the first trial is a success, given that the first trial is a success, is equal to the probability that the second card is a diamond, given that the first card is a diamond, and that is 3 over 51, which is different than the unconditional probability that the second card is a diamond, which is 4 over 52. However, the probability of a trial being successful does not change. It's always 4 over 52 because that's an unconditional probability. So it is possible that you have the trials not being independent, although the probability of each trial being the same. Just by the way, this is called a hypergeometric distribution, not a binomial distribution, but we'll get to that another time. Even more tricky, a well-shuffled deck is cut in half. 5 cards are dealt off the top of one half deck, and 5 cards are dealt off the top of the other half deck. The binomial formula doesn't apply to find the chance of getting exactly 3 diamonds because, again, the answer is B. The trials aren't independent. Okay, the trials aren't independent for the same reason as before. Now, you may think that the probability of a trial being successful changes because in the top half of the deck, there must be a different number than of diamonds than in the second half. However, this is an unconditional probability here, and so we are not specifically conditioning on how we split the deck. But so you could write the probability. So for example, the probability that the first card is a diamond, you could write that as a sum of a bunch of conditional probabilities. You just like we did for the probability, the Bayes problem probability with Greg's eye color at the beginning. So you could write the probability that the first card is a diamond is the probability that the first card is a diamond given that there's 0 diamonds in the first half and 13 diamonds in the second half, weighted by the probability that there's 0 diamonds in the first half times 13 diamonds in the second half, plus the probability that the first card is a diamond, given that there's 1 diamond in the first half and 12 diamonds in the second half, and so on and so forth, all the way up to the probability that the first is a diamond, given that there are 13 diamonds in the first half and 0 diamonds in the second half, times the probability that there are 13 diamonds in the first half and 0 diamonds in the second half. So that sum will actually be a fourth, even though each term here is not a fourth. We're adding together a bunch of terms that will add up to 1/4. So that's pretty tricky. Let me say that if I had said a well-shuffled deck is cut in half with 5 diamonds in the top half, then the probability of a card in the top half being an ace is 3 is 5 out of 26. Yes, 5 out of 26. Right. Is 5 out of the 26, and the probability in the bottom half is probability 8 over 26. So in this case, the probability does change. Then we talked about consecutive odds ratio, which is a tool to find the mode of the binomial distribution. And the mode is the most likely outcome. So here we have the mode is 2 and 3. So NP plus P is an important number for determining the mode. So for example, if NP plus P is 3, you can see you have 3 cases. K, which runs from 0 to 5 here. Either K is less than 3, K is greater than 3, or K is equal to 3. If K is less than 3, then that happens exactly when the stairs are going up. When K is greater than 3, that happens exactly when the stairs are going down. And when K is equal to 3, that happens exactly when we're at the mode. Another example, when we have N is 5, P is a fourth, and in that case, NP plus P is 1.5. And then we don't have the third case because NP plus P is not an integer. So when the floor of NP plus P is equal to NP plus P, in other words, the floor of NP plus P is an integer, then you have case 3. And you have 2 modes, namely the floor of NP plus P and the floor of NP plus P minus 1. However, if the floor of NP plus P is less than NP plus P, in other words, in other words, NP plus P is not an integer, then you don't have case 3 and you just have a single mode, namely the floor of NP plus P, which in this case, the floor of 1.5 is 1. See you next time.